concrete. And have to congratulate Marcel and Jason on one of the best paper awards at FPL. So I thought one of the reasons to have Marcel give this is to give all the new students an exemplary example of some of the work that we do here. So.
Okay, thanks for the introduction. So yeah, the paper that was in FPL is called Reducing FPGA Router Runtime Through Algorithm and Architecture. So the main motivation for this talk is to try and reduce FPGA compile time. So FPGA CAD is getting harder and slower for two main reasons. One is that the FPGA capacities themselves are growing with every process generation, and so the problems that are actually being, or the designs that are being put on the FPGAs are getting larger, which means bigger CAD problems. And then conversely, the traditional kind of compute resource that's been used to run CAD tools, namely single-core CPU or single-core processors, aren't really getting that much faster. So we have kind of this disconnect where FPGA CAD tool runtime is getting worse, and then that increases development time and can even kind of prevent some people from using FPGAs who might use it if the compile times were faster. So how do we reduce FPGA router runtime? Well, there's kind of been two main approaches that have been used for the most part. One is to make algorithmic changes, so you can tweak the algorithm to kind of get some more speed out of it, or else do some sort of trade-off between the quality of the results provided by the CAD tool and the speed of the CAD tool. And then the other approach is to parallelize existing algorithms. So to use multi-cores, which we now have more of. Now our work uses a combination of CAD tool changes and FPGA architecture changes to get kind of a different approach to reduce runtime. Okay, so specifically the work that that I'm presenting focuses on FPGA routing. So FPGA routing is kind of one of the two longest running steps in the CAD process. So in FPGA routing, as well as placement actually, the FPGA is represented as a routing resource graph, where the routing resources, so wires or pins or logic block input and outputs, are represented as vertices. And then the programmable switches between those routing resources are represented as edges. So then the routing problem is really a graph traversal problem. So you get from one vertex to another vertex using the edges, which will be using the programmable switches. The main kind of algorithm that forms the basis for most routing tools, so this is the commercial routing tools in Xilinx and in Altera, as well as in VPR, which is the academic CAD tool that's been developed at U of T, is actually the CAD tool that we're modifying for this work, is the Pathfinder algorithm. So in Pathfinder, signals are routed, and what kind of makes Pathfinder unique is that shorts are temporarily allowed on the routing resources. So that means that different signals can, or multiple signals can use the same wire temporarily. And what Pathfinder does is it makes the routing resources that are kind of more popular more expensive to use. So then with enough iterations, the shortest path algorithm will tend to avoid using those routing resources. And it'll gradually eliminate this routing resource congestion until no shorts exist. So it starts by routing all signals and permitting shorts. So there's no penalty for shorts in the first step. And this is essentially to find the lowest cost path for each route. And then Pathfinder has a good idea of what the kind of popular or overutilized routing resources are. And it increases the penalties for those. And then it starts to reroute the signals, rips up and reroutes each individual signal, and reroutes it with the updated congestion in mind. So these routes will tend to avoid the overutilized routing resources. And then this keeps on going. Signals are ripped up and rerouted until there's no more congestion, so you have a legal routing, no shorts. That's back. This is forward. Okay, so we know that Pathfinder gradually resolves congestion and eventually comes to a short-free solution. But the question is, how fast does it do this? And does it do this efficiently? So this figure here shows the congestion across an FPGA. So the red here is the routing resources that are overutilized. So a lot of different signals are using these routing resources. And the dark blue is kind of the routing resources that are maybe not used at all or only used by one or two signals. And this is after one PathFinder iteration. So congestion hasn't been taken account at all by PathFinder. So what I'm going to show next is an animated version of this as we go through the different PathFinder iterations. And we'll see how this congestion map changes and how it gets better. Okay, so you can see the congestion gets resolved very quickly. You can see the progress on the top there. And to the point where you can't really see any more congestion halfway through. So I'll play this again. There we go. Right, so the congestion gets resolved. Halfway through, there's almost no congestion left. In the last half, it's really just kind of fine-tuning an almost legal routing solution. So PathFinder is very good at quickly reducing the majority of the congestion, kind of making broad changes so it spreads the signals out quite well. But then it spends a significant amount of time just kind of fine-tuning the design and trying to resolve those last few conflicts. And this makes a bit of sense if you think about how PathFinder is actually trying to resolve these conflicts. So I said that PathFinder kind of does it. It allows conflicts on wires, and the way it tries to avoid conflicts in the long run is to adjust costs of routing resources to try and encourage, say, one signal who really needs that routing resource to use it, and then another signal that maybe doesn't quite need it as much to use a different route. But PathFinder spends some time trying to increase costs until the costs are just right so that this is the case. One signal uses this routing resource, one doesn't. And so there's this kind of indirect way that it tackles these conflicts, which works well for when there's a lot of signals, but when there's a few, we might be able to do something a bit better. So what we want to do is use PathFinder, and what we've done is to use PathFinder to remove the majority of the congestion, so just use it to do what it's good for, or what it's best at. And then we're going to do the rest using a different approach. So the way we kind of get PathFinder to essentially exit early is to get it to run on a coarsened routing resource graph. So in this coarsened routing resource graph, each routing resource node actually represents a group of wire segments, so we call them wide wires. So then PathFinder maps sets of signals onto these wide wires. So then at the end of PathFinder, we don't have a legal routing. We have an assignment of, say, 2 signals to a wide wire of size 2. And then we use a separate SAT-based embedding process to resolve these conflicts. So each one of these signals within the wide wire is assigned to an individual constituent wire segment in this embedding step. So before I go further explaining the embedding, let me talk a little bit about how this looks from an architecture point of view. So on the left, we have kind of standard FPGA architecture. We have our logic blocks, our connection blocks, and our switch blocks. And we have 6 wires per channel. On the right, we have the coarsened representation. Now, this is as a routing resource graph in the actual CAD tool, but this is how the architecture would look like. So you can see you have basically 3 wide wires per channel now. And I'd like to look a little bit at the switch block, because now you have, where before you had 6 wires coming into the switch block and 6 going out, now you have 3. So what does this actually look like? So this is a standard switch block architecture, kind of from a coarse point of view, where you have 3 in, 3 out, or just however you want to look at it. And then we have kind of a Wilton switch block topology. Don't worry too much about the switch block topology. The kind of interesting thing is, if you think about these switches in the switch block, they're not connecting wide wires together. So what does that actually mean when we expand the wires out? So now we have, so this is, you have a coarse switch block architecture with n equals 2. That means wide wire coarseness 2, so 2 signals can go into each wide wire. I use n for the remainder of the talk to mean that. So now you have 2 wires going into a switch, and 2 wires coming out of the switch. So what does that switch mean? So we call it a wide switch, and this can actually be represented many ways. So the underlying topology of that switch isn't obvious. So So here I've just shown kind of the most basic underlying switch block topology that we can have, which is just to have direct connections between the constituent wire segments. So if you can see, for example, this wire here just gets turned into 2 wires there. So that's kind of a no area overhead version of this. It's still a slightly different kind of topology, but there's no area overhead. So I'll talk about different switch block topologies a little later in the talk. Okay, so before I get further, again talking about the embedding, this is kind of the potential benefit to routing runtime. So this shows the runtime of just the Pathfinder step, not including the embedding step. On the y-axis is routing runtime. You can see it starts at 7 seconds, not 0 seconds, so it doesn't go to 0 with coarseness 5. And then coarseness goes from 1 to 5. So when coarseness is 1, it's just the standard Pathfinder algorithm, standard routing architecture, and at the end you have a legal routing solution. And as you go further to right, we have kind of larger wide wires. So you can see when you go from n equals 1 to n equals 5, we can reduce routing runtime in Pathfinder by about 50%. So the key now is to try and make an embedding step that doesn't eat away all of that benefit. Okay, so the embedding step is the problem of assigning signals within wide wires to individual constituent wire segments on the FPGA to come up with a legal routing solution. Now all those possible embeddings are constrained by the coarse routing that's been generated in Pathfinder. So we can't make changes in the embedding that alter that original coarse routing. So it's a fairly constrained problem. And we formulate it as a SAT instance. So a bit of background on SAT. SAT is, a SAT formulation is just a Boolean formula where if that Boolean formula is said to be SAT, if there's an assignment of true or false to each one of the variables within the Boolean formula, so that the overall formula is equal to true. It's unsat if there's no such assignment. So an unsat Boolean formula will just simplify to false. So for example, f equals a or b, that's sat because you can have either a or b equal to true, and that would make that equation sat. The equation below, you can try and figure it out, but there's no assignment of true or false to a or b that will make the overall equation true. That equation is basically f equals false. So for our SAT formulation, we generate a set of clauses, SAT clauses, that represent all the routing constraints given the coarse routing that's been generated by Pathfinder. And then we solve these constraints using Minisat. And then Minisat, when it solves these constraints, we get the legal routing out. So I'll talk about the formulation itself to convince you that this is true. But there's 2 types of constraints that we generate, or clauses. One are exclusivity constraints. So the exclusivity constraints ensure that there's no shorts on signals. So essentially no 2 signals use the same wire segment. And then the liveness constraint ensures that there's a live path from each source to sync. So if you took away the liveness constraint, one easy solution to this is to just don't do any routing, and then you don't have any problems with exclusivity. So we need the liveness constraint to make sure the SAT solver actually does some work and does the routing. So the actual variables that we use for the SAT formulation, there's a variable for each signal to wire segment assignment. So if that variable is true, it means that that signal uses the wire segment, and if it's false, then it means the signal does not use the wire segment. So at the end, when the SAT solver is done solving the instance, we have an assignment of true or false to each one of these variables. So we know which wire segments each one of the signals uses, but just by looking at the true variables. Okay, so here's an example of an exclusivity constraint. This is kind of a subset of the overall problem, and we do this all across the FPGA, but we have one wide wire with n equals 3, which means that 3 signals can be put onto it. So wire 1, 2, and 3, and we want to put signals A, B, and C onto these wires. So we want to make sure that no 2 signals use the same wire. So these are the constraints that we would generate for wire 1. That's not right, there should be some knots in there. Okay, well there should be basically not on top of all of the variables there. So not A1 or not B1, not A1 or not C1, not B1 or not C1. Sorry, yeah, so let's look at the first one, not A1 or not B1. That basically means that if A1 is true, then B1 has to be false, because at least one of A1 or B1 has to be false for the clause to be true. And the same with A1 and C1. If A1 is true, C1 has to be false. So this ensures that only one of A, B, or C, only on wire 1, so A on 1, which is A1 represents signal A using wire 1. Should have mentioned that. So only one of those variables can be true. Okay, sorry, does that make sense? So that's the exclusivity constraints. And for the liveness constraints, those clauses are actually right. This ensures that A, for example, so in this case, A1 or A2 or A3, makes sure that A uses at least one of wire 1, 2, or 3. So you can't have the case where A uses none of the wires. And so if you take this across kind of the whole path of A, this ensures that there's going to be a live path from the source to the sink. And then the other type of liveness constraint, so this is kind of to make sure there's valid connections through the wires, and then the other type is to make sure there's valid connections through the switch blocks. So it's important that, so not all underlying switch blocks are present, or sorry, not all underlying switches are present, as I've indicated in the architecture description. So we only had kind of the straight connections. So some connections aren't valid, and we want to make sure that it's not assumed that those connections are there. So for example, here we have an expanded wide wire on the left, again with n equals 3, and an expanded wide wire on the right, again with n equals 3, and we have a wide edge that's connecting them. And so this is the underlying switch block topology. We just have our straight connections. So we want to make sure that we don't make any connections between, for example, A1 and A3. So signal A using 1 and signal A using 3. And same goes with A1 and A4. All other connections for signal A1 are valid. So the clauses that we would generate are these ones. We want to forbid both A1 and A3 from being true, and we want to forbid both A1 and A4 being true. So one of those signals within those pairs has to be false. So that's all for the constraints. And then if we AND them all together, we get an overall Boolean formula that we can solve. And if it's solvable, if it's SAT, then we have a legal routing solution. And if it's unsat, then there's no embedding that exists, given the coarse routing that's been generated and given the routing architecture. Okay, so we started doing experiments just with this basic switch block topology with one-to-one connections, no area overhead. And what we found is what we got unsat for almost all of the benchmarks we tried. So it turns out that there's not enough flexibility left once you constrain the problem using the coarse route for the SAT solver to play with to come up with a legal routing solution. So we have to actually play with the routing architecture a bit to get this to work. So we're playing with the underlying switch block topologies. Okay, so what we did is we added extra switches to the underlying switch block topologies to try and reduce the likelihood of SAT, with the hope that we could add only a few and get kind of SAT across the board. So we used, in our experiments, we used a single switch block architecture, used that across all benchmarks that we tested. And I'll explain my experimental methodology in, I think, the next slide. And if it was SAT for every single benchmark, we said that architecture was successful. And if it was unsat for at least one benchmark, then it's unsuccessful. And then so we explored a range of switch block architectures, around 2,000 that we generated, which is not that many given kind of the overall solution space, but anyways, it gave us some idea. And what we found was that there were actually some low area overhead switch block architectures that get SAT across the board, and they're quite good. We might still look into kind of more switch block architecture, more than 2,000, to see some more good switch block architectures. But this is just one example of the switch block architecture that we got for n equals 3. So here we have unidirectional wires, n equals 3, and we've omitted all the one-to-one connections. So in all the switch block architectures that we explored, we had at least one-to-one connections because we found that if we didn't have those, we basically had situations where there was no possible connection between two wires. So we had at least one-to-one connections. And these are the extra switches. So what you see here is essentially full crossbars in the vertical and horizontal directions, and no extra switches in the turning direction, which is an interesting result. This is kind of the best switch block that we found. And one reason for this might be that, in general, the VPR routing algorithm, or Pathfinder, tends to use straight connections more than turning connections. So the extra switch block added in these directions just we're able to use them more because more signals use them. So this is a smart way to use our extra area overhead. So this is our experimental methodology. We use the 16 longest running benchmarks in the MCNC benchmark suite and in the VPR5 heterogeneous benchmark suite. So we did coarse routing using Pathfinder, and then using that coarse routing and using the switch block topology, we generated a SAT formulation, put that through Minisat, and got our routing solution. And then to be able to compare critical path and area numbers, we put it back into VPR just to do timing analysis. So we didn't do the routing step and didn't change any of the routing. We just got some results from VPR to make sure that the results were good. Right, and here are the kind of summary results. So on the x-axis, again, I have coarseness. On the y-axis, I have runtime like the last time. And now I have the sat time kind of stacked on top of the routing time. And you can see that n equals 3 gets the best kind of sum of runtime for Pathfinder and the SAT. And for that particular architecture that we used that I showed you, it was around the 3% area overhead overall. So we're able to get a 35% improvement in runtime with 3% area overhead. And the nice part is there's actually no impact to critical path delay from doing this because you have all of the timing information, almost all of it, in the Pathfinder step. So, yeah. Okay, so kind of there's two components to the improvement that we saw. One is the improvement that we got from using our method, and the other improvement is just this kind of natural trade-off between area overhead and runtime for CAD. So if you increase the amount of area that you have on an FPGA, probably you'll get an easier problem and you'll just get reduced runtime. So what we wanted to do is explore different methods that we could trade off area and runtime and compare against that to make sure we're better and we're not just taking advantage of an area runtime trade-off. So the first experiment we did is we used our modified switch block architecture with the extra switches in the switch blocks and ran VPR Pathfinder without the coarsened routing resource graph and without the SAT step, and then compared the runtime against that. So the idea is there's extra switches, it should be more flexible, we should be able to make connections that weren't there before, and so should have an easier time of routing. And then the second experiment is to compare against kind of a well-known way of trading off area versus CAD runtime or routing runtime. And this is kind of the first thing people think of is to increase the number of tracks per channel. So if you have more tracks per channel, you're going to have an easier routing problem and you're going to have reduced runtime. And it's been explored and that is the case. Okay, so compared against each one of these methods, in the second one, we increased the number of tracks per channel until the area was equivalent to our method. You could equally think of it as decreasing the channel width of our approach until it was the same as the standard architecture. So these are both kind of area neutral results. So in the first one, what's surprising is that there's no change. We still get 35% faster than Pathfinder when it uses the modified switch block. And this is interesting because if you were to look at this experiment in isolation and just say, let's say you wanted to explore the effect of increasing the flexibility of your switch block on runtime in the routing, you would run this experiment and say, oh, there's no effect. There's no impact of changing the switch block architecture. So that's useless. We don't want to explore that. When in effect, what you have to do is actually change the algorithm to directly make use of that switch block. So this kind of underlines the need to look at architecture and algorithm together when you're looking at CAD runtime. And then the second experiment shows that yes, increasing the number of tracks per channel does improve runtime, but not as much as our approach does for the same area. So we still get 21% better area for an area, 21% better runtime for an area neutral result. Okay, the last kind of result slide is just showing SAT scalability. So the first thing that people think of when you say you're using SAT is that it's going to be slow, and if it's fast, it's because your problem's not big enough. So this slide shows the number of clauses and the number of variables for the SAT instances for all of our benchmark. So you can see it's linear for the number of clauses and the number of variables. So it doesn't get the complexity or the runtime grows linearly with the size of the benchmark, which is desirable. The very biggest benchmark has about 1 million routing resource nodes, so that's kind of the extent to which we kind of experimented with this. Okay, so just to conclude, we looked at two-stage routing, where the first step uses a PathFinder-based routing operating on a coarsened routing resource graph around wide wires. And then the second step looks like add a SAT-based embedding that resolves the leftover conflicts. We get a 35% runtime improvement when taking the 3% area overhead hit, and then a 21% runtime reduction with a 0% area overhead in our area neutral results. The thing that I find kind of exciting about this is just that this is an approach that you wouldn't have been able to consider if you had looked at only FPGA architecture or only CAD algorithms. So it's kind of an interesting area of research looking at both of them together and seeing how you can come up with new approaches to reduce FPGA router runtime or CAD runtime in general. So we'd like to, and something we're currently working on is exploring more low-level switch block architectures. So kind of 2,000 switch blocks is a very, very small subset of the overall solution space. So we're looking at kind of hundreds of thousands to try and see if we can get some idea of what makes a really good low-level switch block. And also looking at whether we can actually make changes in the VPR PathFinder algorithm to see if we can preemptively kind of avoid unsat solutions. So other than operating on the coarsened routing resource graph, we haven't made any changes to the costs in VPR PathFinder. And so we think maybe we could make some changes to those and generally kind of make it aware of whether it's generating coarse routings that are likely to be SAT or unsat, and hopefully we can get some better results that way. So that's it for the talk. I'll be happy to entertain any questions.
Race condition. As maybe relates to your coarse graph embedding, are you using the bend cost that's in VPR? There's a cost to make a jog that can be set. So then it prefers horizontal routes or vertical routes with a minimum number of bends. So that
I'm not sure. Do you know if that's default or not?
It's not on by default, but it basically would. It seems like it would help you with your switch block, which prefers horizontal or vertical connections. It basically makes, exactly as you're talking about, it makes the coarse embedding aware of that desirability.
No, I'm not using the kind of, I didn't know that was there. I'm not using the built-in one. I did try kind of putting in my own cost that would prioritize kind of straight connections, and that helped a little bit, but hurt routability a little bit, so it ended up kind of being a wash as to whether it was actually an improvement in runtime or not. But I haven't looked into actual built-in bend.
It's probably works the same way. It's pretty simple.
Okay.
Just adds a cost for turning. So
yeah.
I guess another question I have, still for more. Are these all unit length wires?
No, sorry. They're length 2 wires, yeah. There's no reason that it shouldn't work for also a mix of wire segments, but just to keep things a bit simpler, we use length 2 wires.
Thanks.
Or I should have. Yeah.
Just wanted to ask you a question about the wide switch block. So when you go to n equals 2 or n equals 3, you don't add any specific routes in there, just the initial slides that you were showing around slide 17 or so. Does that mean that the number of SRAM bits required to configure that switch block goes down by a factor of 3?
No, I mean, if you look at the architecture, the switches are just kind of arranged a bit differently. You're not actually reducing the number of switches, and
Well,
and
not the
they're
number of
going in different
switches.
directions.
Okay, not the number of switches, but the number of bits required to control those switches.
No, because they're not, I guess, no, it's not bus-based routing.
Okay.
So that's, I guess in bus-based routing you might get that, but you can't, like you're not actually getting any improvement with that.
Okay, so you're not saving any SRAM, basically.
You didn't talk about timing?
Critical path delay.
Yeah.
So,
Or did you do it and I missed it?
I think I said maybe half a sentence about it. It doesn't get worse. So you think it might get worse because the fan-out kind of increases in the switch blocks, and we modeled that and it didn't have any appreciable impact. It was maybe at worst, well, sometimes it got better just because of noise, but at worst 1% for some benchmark, worse.
Question from Benjamin.
Okay.
Says, I'm curious if you're taking full advantage of the PathFinder to resolve most congestion at the detailed routing graph. Would it make sense to run PathFile on the detailed graph and just fall over to SAT when there's still congestion?
So that would be nice. I can't think of a formulation that would make that work. I thought about kind of how to kind of use SAT to kind of resolve kind of spot, like do kind of spot resolution, and I can't think of a formulation that would work. Yeah.
If you end up with an unsat after your coarsened routing, is there any recourse, or are you just
There could be.
out of luck?
There could be. I mean, I haven't built one in because it would be extra work, and I don't. But you could. For the simplest thing is just to rerun it, and then just don't use the coarsened routing resource graph. And so, kind of, let's say 1% of the time you get an unsat solution or something. 1% of the time you'll double your runtime. A much smarter approach might be to actually provide feedback back into Pathfinder and get it to say, save the state 3/4 of the way through or something, and then say, well, actually, the tweaks you make at the end, could you actually make slightly different tweaks? Something like that, but I haven't built that in. Yeah.
Are you using a direct drive architecture?
Yes.
So so if a wire goes right through the switch block, you basically treat that as one pacifier and you don't touch it. And so you span it out, you only expand it if it ends or starts at the switch block.
So you have to group wire segments into wide wires carefully. So you have to group, maybe I'm not answering your question. Let me say this and then you can tell me if I answered it or not. So for example, when n equals 3, you have to take groups of 3 wire segments that start and end at the same spot and that are going in the same direction and group them together. And then once you do that, you treat that wide wire just like you would have treated the wire segment in an uncoarsened routing resource graph, except that it has a higher capacity for signals.
So the plot you showed about the reduction in router runtime as n increases, what's the relative importance of a reduction of the number of iterations versus each iteration getting faster since there's a smaller graph?
I guess you can't kind of tackle one without tackling the other. I don't know. Your question is like basically, what should you focus on? Should you
No, I'm saying is that it's a pure, what were your results? The router can get faster if you run fewer iterations, or it can get faster because there's a smaller graph and it's making fewer heap ops or decisions on which wires to choose. So what's the relative importance of each of those factors that it contributes to the runtime reduction?
Okay, yeah. So I think, and this is just from memory, that there's maybe like a 15% reduction in runtime that comes from the smaller routing resource graph, and then the rest maybe is from having fewer iterations, or having so I guess the other thing is the version of VPR that I'm using doesn't rip up and reroute signals that don't have congestion on them, so then the iterations get faster because you're looking at fewer signals as well.
Could you actually reduce the number of iterations as well? Like you experimented with that? You turned it down until it didn't work?
No, like the number of iterations that typically had to occur before you came up with like a legal solution, legal being n signals on a wide wire size n. That was slightly less than when it was run on an uncoarsened routing resource graph. So there's a reduction in the time of each iteration and also a little bit in the number of iterations. Any other questions? Yeah.
Just that video you showed
Yeah.
on congestion, what's the metric? What does the red represent?
It's the occupancy of the routing resource node. So the number of signals that are kind of temporarily assuming that they have control of that routing resource node. Red would be, I don't have the exact number, but higher than, I don't know, 10 or something like that. And then blue is like 1 or 2, or I don't know, I scaled it to kind of the range that I saw to try to get a, yeah.
Okay,